All right, well, it is 11:36 by my clock, so we'll go ahead and get started. Welcome to the faculty outreach lunch for Microelectronics and Nanotechnology research area. I'm Andrew Lake, Mallet ain't working. I am Andrew Lake, the committee chair for faculty outreach with ECESS, and I'm a junior in electrical engineering. Also have minors in history and material science. My primary interest is semiconductors and their manufacturing. If you'd like to go ahead, everyone would like to go ahead and introduce themselves, that'd be great.
All right, I guess I can start. My name's Jared. I'm a sophomore in electrical engineering, and I don't really know what I want to do yet, but I'm hoping to help figure that out.
Hi, I'm Edmund. I'm in a similar situation as Jared. I'm also a sophomore in electrical engineering, and I'm excited to see what you guys have to say today.
Hey everyone, I'm Sam. I'm a sophomore in computer engineering. We're snowed in today, and I got the email saying this was going on, so here I am with my bowl of enchiladas, and I'm excited.
Hello everyone, I'm Ryan. I'm a junior in computer engineering.
Hello, I'm Nick. I'm a junior in electrical engineering and I'm focusing on microelectronics.
Hi, I'm Rohan. I'm a freshman coming into electrical engineering and a minor in CS. And I'm not sure whether I want to go down the math CS route in ECE or the physics route, so I want to explore both.
Hi, I'm JD Conway. I'm a sophomore in electrical engineering and minor in chemistry, and I intend to focus in microelectronics and nanotechnology.
Okay, I'll go. Hi, I'm Matthew. I'm a junior in computer engineering.
I think that's all students on the list. My name is Zhihong Shen. I guess I will give a short presentation later, but I'm a professor of ECE, especially in the microelectronics and nanoelectronics area. So I'm very excited actually to join this event. I want to see students interested in our area, and I would like to share my experience with you.
And we will have more professors joining us later. A few of them know that they'll be late.
Mm-hmm.
So to start us off, I suppose I'll just open the floor to general questions if anyone has anything. Otherwise, I can start a discussion and we'll go from there. All right, so Professor, why don't you tell us a little bit about microelectronics and nanotech and what it's all about?
Mm-hmm. I even prepared a little presentation. So like if you guys are more interested in details of the research, I can share the slides. But first, this is the conversation actually I'm looking forward to have with you guys. Like through different platform, I hope that we can meet, like especially like the students interested in the semiconductor career, because this is a golden time. I would say you guys are really at the right timing for a career, developing career in this area. So like I would say semiconductor industry has been there for the last half century, right? And we know that the computers, like all the electronics has been developed really like to this extent that everybody has an iPhone, has a smartphone in your pocket, that we basically carrying a computer every single day in our pocket. And like for a while, I think there's kind of like impression that the hardware is almost done, because people are claiming that the Moore's law has been finished, has reached its end. And then everything that you can do to improve computers is about the softwares, about the maybe at the architecture level, you can do something. And so we see that many students actually are like jumping to the computer engineering direction or even going to the CS direction. But actually in the last 5 years, like through my own research funding and my own research field, I realized that things have changed again. So it's true that my research has shifted or at least expanded from covering nanomaterials and nano devices actually now into like a covering system level type of computing schemes. But I see that for our electrical engineers, we can really like have our device knowledge, our circuit knowledge being applied to new type of computing. And the industry actually really needs these new computers in order to solve many more new problems that were not under consideration in the past. For example, that we have a program called probabilistic computing, and these new computers that we would like to build will be able to solve problems that the classical computers can never solve. Some of you guys probably have heard of quantum computer, and quantum computers, like if they ever get built, they will not be in a pocket, right? Because this will be operating at like a millikelvin temperature that probably it will be on the cloud. And only like companies or really large scale problems will have access to the quantum computers. And so like the semiconductor industry actually is very interested in developing new type of computers that can solve many other like day-to-day life problems. For example, nowadays we are like working with the car industry, trying to see that for autonomous cars, what can we do to improve the computing efficiency? Because when atomic cars need to make decisions, it needs to happen at the millisecond level. And you cannot wait until the communication to the supercomputers or to the quantum computers to tell you which route is less jammed in a very busy city, like which route actually has an accident that you should avoid. Or like these days for Amazon trucks, when they try to deliver products nationwide or even worldwide, what is the best way, most efficient way for them to design their delivery path? All these things actually we call like these problems are on the probabilistic side, because you never know at a given moment what's the next status of your problem. And so for this type of problems, you need to develop new computers. That's why I say nowadays, again, there are so many opportunities for our electrical engineers to discover new physical phenomena so that we can build new computers upon these new phenomena, and also develop new engineering platforms that we can really put these things into production. And also our nation actually is investing a lot of money into microelectronics. The federal government recently passed a bill called the Chips for America Act bill, that we are having $30 billion investment into hardware development of microelectronics for our country. And so there are just tons of jobs. Nowadays, like I have multiple companies coming to my group asking for my students to join them. So if you guys decide to come to our microelectronics areas, you will have a lot of job opportunities and career opportunities. So it's not only just a job. I think there are a lot of opportunities actually for research and for really technology development. And I'm personally very excited about this new phase of our field. And I hope that it's really opportunity for you young guys to develop a career. So that's my pitch to you guys to join our field, basically.
I do remember seeing that in the news recently, that there was a, I think open letter would be the correct phrase, from a bunch of different US-based companies basically asking the president, hey, we want to manufacture chips on US soil. And I believe, is it TSMC is building a new fabrication plant in Arizona? I remember they were recruiting for that the other week.
And we actually, our Purdue also has a center, actually TSMC funded center that we are working very closely with them on the design side. So these are foundries for microelectronics. And we also have our own company, domestic companies like Intel, like Micron, all these larger companies actually we are working with.
And sorry, a little bit of background for people who don't know who TSMC is. They're the Taiwanese Semiconductor Manufacturing Corporation. Is it corporation or company? I believe it's corporation. And they manufacture a very significant percentage of high performance computing things. And there's not that many players in the manufacturing industry. There's basically TSMC, Samsung, Intel does their own fabrication, Micron, as you mentioned, SK Hynix as well.
Yeah, like Andrew, you are completely right. Like, so the TSMC and Samsung, they are actually called foundries. So these are the companies that even Apple or Google, they can send their chip designs to them. So Apple and Google, they can act as fabless companies. So they can have their own chip designers, and then they send their chip designs to TSMC to get their chips fabricated. So I think the Apple M1 CPU is in this way, designed by Apple by itself, not by Intel anymore, right? And while Intel is a semiconductor company, it's not a foundry. So they only produce their own designs, their own chips. They are not making chips for other companies. So that's the difference between a foundry and a semiconductor company. So Intel, IBM, they are the traditional semiconductor companies, while TSMC and Samsung, they are like providing services, providing their technologies to all other companies.
And I know you mentioned you did have a little presentation. I can give you screen share privileges if you would like to share that, or we can go to
if
questions.
anyone has a question, you can interrupt and bring it up. I don't need to go through the very rigid.
Yeah, there is a question in chat here from Jared. He says, earlier you mentioned that people think Moore's law is ending. Is that because transistors are getting too small?
Yes, so that's actually part of my presentation, and I can share my slides and we can discuss that a little bit more. That's actually part of my research that I have been pushing for in my career for the last 15 years. Where's my share? Okay, share. Do you guys see my screen?
Yes, we can.
Okay. Yes, so I will talk about the Moore's law ending probably in the next few slides. So a quick self-introduction. So I'm a professor in ECE, like actually, especially in the microelectronics area. That's our the area called MN, micro and nanoelectronics area. That's where my main field is. And also, since 2019, I have been serving as the Associate Director of Research for the Berkeley Nanotechnology Center, which I will also give a little bit of introduction. And you guys are in junior, most of you guys are in junior years. So you should actually come to Berkeley. Like, we have the best facility in the country for universities. And if you would like to have some type of undergraduate research, I think this is really a wonderful place to work. And on the bottom, I have the Berkeley building picture. Actually, it's a very nice facility. So this is a quick, just a quick introduction of myself. So you can see that I got my PhD in physics in 2003. And I was actually a physicist. So I wouldn't have encountered with you guys in my career path if I stayed in physics. But after my PhD degree, I actually joined IBM. That's why now I become an engineer instead of a physicist. And I was first doing a 2-year postdoc at IBM TJ Watson Research Center in Yorktown Heights, New York. And then I stayed there as a research staff member for 2 years. Then I became the manager of the carbon technology group at IBM. And after another 2 years, I decided to join academia. Then I came to Purdue in 2010. And so this is almost the 11th year of my career at Purdue. And so just now the question was talking about the ending of Moore's law. So you actually can find probably in EE Times, this journal that a lot of, this magazine that a lot of engineers actually read. And about the 2019, there is an article to say declare of Moore's law, end of Moore's law. And the reason is exactly what you asked in the question. Because of the size of the transistors are reaching few nanometers now. So I think the TSMC is the one that this year declared that they are doing research on 3 nanometer transistors. And you can imagine after 3 nanometers, maybe you have one more node, 1 nanometer, that's about it, right? We are talking about just really few atoms in the channel, and you cannot do better than that. So that's why it is exactly the size that we have pushed the transistor to that kind of ends the Moore's law by itself. And what is Moore's law actually, like because I'm teaching 255, which is the last semester of 255, and I'm also teaching 305. I have used this chart quite a bit in my 2 classes. So if I think most of you guys have heard about the Moore's law. Moore's law is not a scientific law, right? It basically says the number of transistors in the IC chip should double like every 2 years. So it's a kind of business decision. And this Dr. Moore actually was one of the founders of Intel. So he basically told his company, hey, you guys need to work really hard to make the number of transistors on the chip double every 2 years. And the semiconductor industry has really rigidly followed this Moore's law, this requirement. You can see that the number of the transistors just kept doubling. And 2013, that's our iPhone 5S. I don't know if any of you guys owned this iPhone back then or not. This picture on the left top side here, this is A7 CPU inside of iPhone 5S. It had 1 billion transistors. And then here, this is the transmission electron microscope picture. So on the bottom, these little dome-looking ones, these are the transistors, and we have 1 billion of them on the bottom of the chip. And on the top, there are a lot of these almost like teeth type of looking things. These are the vias and the interconnects. And we have like 8 to 11 layers of interconnects on top, which actually can, if you connect all these copper interconnects together, these are 28 kilometers of these copper interconnects. So that's how complicated our computer chips are these days. But then, like now, if you look at 2011, like we have an A13 computer chip. I don't have a picture of A13, and we already have 8.5 billion transistors on the chip. And so every 2 years, you can see like there are 6 years here. That's why from 1 billion to 2 billion to 4 billion to 8 billion. Right? So we are still following Moore's law very, very well. And but then after 2020, like if TSMC really reaches their 3 nanometers in another 2 years, how much room, how many more generations that we can still have is really, really questionable. Maybe 1 or 2 more generations. And so like besides the number of transistors have been this following this Moore's law doubling all the time, the sizes of the transistors obviously have decreased because we are not trying to make the chip larger and larger. That's not the point, right? You keep the same chip areas, but you need to fit more transistors in. So these days, current technologies, we are talking about the 7 nanometer transistors. These are already in production. And the TSMC is talking about the 5 nanometers, so almost ready, and the research on 3 nanometers. And so like this decreasing of the transistor size has been in the research field for many, many years. And so you see that I'm going to quickly cover the 2 research areas that I have been personally involved. One is to make the, One is to make the transistors smaller and smaller. Like you see that the silicon transistors are reaching 5 nanometer channel length. And here in this picture, I don't know why I don't have this. In this picture that you see that for this transistor, there is a gate here. and there is a gate dielectric. The gate dielectric is already reaching 1 nanometer thickness. That's why I say every dimension in these devices has been pushed to very close to the limit, right? And besides these 1 billion transistors at the bottom of the CPUs, I also mentioned that we have 8 to 10, or these days maybe even to 12 layers of these copper interconnects on the top. Because in order to make 1 billion transistors into functional circuits, you need to have all these interconnects. And the 1 billion of them, like you cannot have the wires running at the same level. So that's why like 8 to 12 layers of these wires need to be connected through vias in order to like connect all these billions transistors on the bottom into circuits. And then when we are trying to push the transistor size to be 5 nanometers or below, you can see that these copper interconnects or vias also need to be scaled down accordingly. And these days we are talking about the copper interconnects also into sub 20 nanometer range. And in this TEM picture, you can see that this is a cross section of the copper interconnects. And the copper actually can easily diffuse into the surrounding areas. So the industry actually has been putting down a layer of materials called the diffusion barriers, tantalum nitride diffusion barriers to block the copper diffusion. Otherwise, you get all your entire chip actually being shorted. And so we are talking about scaling down the transistors to be smaller size. We are talking about how to make these interconnects and vias to be smaller, at the same time preventing copper diffusion, preventing all these reliability issues. And so this has been the research that many of us, including myself, have been devoting our career, our interest to. And for example, one of my research areas is in this copper interconnects area. The current problem is that the industry is using tantalum nitride to block copper diffusion. And when the copper interconnects are big, it's not a problem, right? And you can see in this picture, you still have the majority of the cross section being occupied by copper. But once your copper interconnect size needs to go down to sub 20 nanometers, you see the problem is now in this cross section, my total width can be 20 nanometers, but I still need to leave some room for the diffusion barriers, like a tantalum nitride diffusion barriers. And so only like in the very middle, I can afford to have copper. And the copper is used as an interconnect because it's very conductive, while tantalum nitride are not. And if you have something mixed in your interconnect lines that are not conductive, obviously you are going to be much more resistive. You are going to cause much more larger voltage to operate your circuit, and you are going to waste a lot of power, right? So this has been actually becoming the bottleneck of our CPU's performance. Like a few years ago, actually, people have seen a picture that on computer chip, like the temperature has risen so much that you can even cook an egg on a computer chip, exactly because of this passive type of power consumption, not because of the transistors. Transistors are constantly being turned on and off. Most of the time, actually, most of the transistors are off. They are not constantly being on. But these copper interconnects, they are constantly passing currents in order to have the circuit operating. So these guys actually, although they are not the active elements, but they are consuming a lot of power. And so like a part of my research actually is to identify new materials that can replace this tantalum nitride layer, because this layer is so thick, and at the same time it's so not conductive. It's really the problem. And so my research has been looking for new materials that we can replace these conventional materials to block the copper diffusion at the same time, like the body thickness is very, very small, so that we can recover the copper interconnects performance. And there is a field called a two-dimensional material field, 2D field, which is very, very hot in the research field these years. Since 2010, like graphene was discovered and earned the Nobel Prize. This field has been really hot. Many researchers are jumping in. And I'm part of the field that looking for applications of these 2D materials. And this is one of the applications that I identified, that this one layer of atoms can block copper diffusion very, very efficiently. right? So we are really talking about the body thickness of 0.3 nanometers of graphene or 0.7 nanometers of molybdenite or other transition metal decoordinates. So these atomic layer thin materials are able to do the job. And so that's for the interconnect part. And for the transistor scaling, we are also looking for new materials, maybe not to completely replace the 8 billion silicon transistors, because that job is too challenging, to be honest. We have how many millions of engineers in the semiconductor field working on silicon transistors. For any other materials research to replace that computer chip at that scale is very, very hard. And so nowadays, we are very often talking about the new materials, new transistors to enhance what the silicon has been doing, or maybe add more transistors at the back end of line with the interconnects, with the copper interconnects in order to enhance the functionalities of the chips. And these are some of these 2D materials. For example, here on the left-hand side, you can see again another transmission electron microscope picture. Here we are talking about a device, like this is a gate on the top. Maybe I should use my laser pointer here. There's a gate on the top, and we have the gate dielectric, and there is 3 layers of this tungsten disulfide. And here we are talking about the 0.7 nanometer per layer. We can actually scale that down to really single layer of these atoms, tungsten disulfide atoms, as the semiconductor channel here. And the beauty of these 2D materials is that their body thickness is so thin. When silicon comes to this 0.7 nanometer body thickness, silicon almost cannot conduct current anymore, while these materials can, right? And at the same time, in order to make 3 nanometer transistors, if you don't make your body thickness really, really thin, you are going to lose your performance. That's why silicon, to scale down to 3 nanometers, it's not only about to make your device small. TSMC also needs to make sure that the silicon body, like in that 3 nanometer transistor, still can deliver the right on current and the right off current in a transistor. If you guys have taken 305, you should know what I'm talking about. We are looking for a switch that can be turned on with very high current and can be turned off, not consuming much power, right? So it's a switch with on-off ratio. And the silicon at 3 nanometer, it's extremely challenging to reach this type of performance, while these 2D materials can easily reach because of their body thickness is very, very thick. And also because of they are naturally layered materials, you can see here, I can also show through some chemical treatments, you can completely atomically etch the layers. I have a 5-layer tungsten diselenide here. And after some treatments, I can convert it into 2 layers with almost atomic sharp type of interface. Right. So there are a lot of material science that you can discover and manipulate with these materials. And there are a lot of device, like fabrication device design and engineering that you can do to keep high performance for the transistor applications. And so these are some of my students actually fabricated and measured. So this is a device with 40 nanometer channel length. And with 40 nanometer channel length silicon, it's already showing much worse performance than our 2D materials. That's why we published this paper in IDM, one of the top device conference, and the TSMC researchers got very excited because they haven't seen such a nice off-state performance actually from the silicon devices. Right? So these are the materials research and device research that we are providing to the semiconductor industry. And there are also other materials, like for example, back in IBM time, I was working on carbon nanotubes. IBM was for 10 years thinking to push carbon nanotubes to replace silicon. That was a very serious business decision, but it didn't work out eventually because of the material issues that to place 1 billion of these below 1 nanometer carbon nanotubes, the diameter is below 1 nanometers, right? To place them exactly where you want and with the desired density, the material issue again was the biggest challenge. That's why IBM didn't succeed in making nanotube computers eventually, right? But we actually spent almost 10 years of our career on this material trying to push for the device and push for the transistor scaling. And there are also many other materials like graphene was researched. Even now, still graphene is a very hot topic in the 2D fields. And these days, many people have focused on transition metal dichogenides, the tungsten disulfide, the tungsten diselenide I mentioned are all in these the material categories. And the last topic I would like to discuss actually is probabilistic computing. So just now we were all talking about the conventional computer chips with the transistors at the bottom and the interconnects on the top. And we are using these conventional CPUs actually for general purpose computing. And as I mentioned, if you don't have the materials and the devices scaled down correctly, these chips can be very power hungry and can really even cook an egg, right? Instead of doing your computing job. And then one thing that I also want to introduce a name here, our computers are very precise. Normally you trust your computer 100%, right? When you ask it to do any computing jobs, you have no doubt that our computer can do the job. And so we call it actually deterministic computing. It can do precise, accurate computing very well. And nowadays we are not considering to build another computer to replace this type of computers, because our computers, silicon-based computers are already doing wonderful jobs there. But there are many other problems that we need actually new type of computers to solve. For example, the travel salesman problem or Amazon's truck, how to design the route smartly that the travel salesman or Amazon's truck can actually travel among 1,000 cities with the shortest distance. This is actually a problem which we call NP-hard problems. It's very hard. Once the number of the cities increases, these problems becomes really difficult to compute for traditional computers, right? So this is a famous NP-hard problem for travel salesmen. And also there are many predictive type of problems, even for your loan, like should your loan turn itself on, depending on if the day has, it has rain or not, if the grass is already wet or not. These are still on the simpler side, but you can imagine many other problems nowadays in nature, in our human societies are becoming more and more complicated, like this time the COVID virus. How should the virus, if you identify a few local cases, how it will spread out? What type of probabilities when people travel or not, when people are quarantined at home, what is the probability? All these things actually can be kind of computed or at least estimated to some extent, right? And again, these type of problems are not our current computers best, like our computers actually are not the best candidates to do this type of computing. And there are also other types of problems that computer scientists are very interested. For example, invertible logic. Our computers can do multiplications, but cannot do factorizations very nicely. There are algorithms to do factorizations, but once I give you really large numbers, it's very, very hard for our classical computers to factorize really large numbers, right? And so these type of problems, actually, there are proposal from Professor Superior Data. We are very lucky to have Professor Superior Data in our department. And he's definitely a guru that I learned from his textbook when I was a student. And so he has proposed a new type of computer called a probabilistic computer, that we are not building these normal transistors in our computer chips anymore. We are trying to make a random number generator as the basic computing element in our computer. Every element should be jumping between two states with 50% probability. And then depending on the input you give to this element, it can pick one of the states more preferably. For example, here I have up states and down states. And right now, without any inputs, it will just jump between the two states with the equal opportunities. And so these days with our societies really having a lot of data to analyze, a lot of situations like our cars or our electronics would like to have fast decisions. You can see actually really tremendous increasing needs of a specific computer specific computation powers actually to solve these problems that were never like occurring in the past. And there are actually new ways that we are trying to solve these special probabilistic type of problems. We are no longer trying to do 1010 type of binary type of computing. Actually, you can treat every complicated problem as a physics problem. And you try to say, I calculate the energy states of my physics problem. So you can always map your problem into a physics hardware. And if you have taken some physics classes, you know that every physical system has energy states, and you can always find the minimum energy state. And you know that every system wants to naturally go to the minimum, the ground state of the energy states. And if you this is so-called annealing process, that if you allow your system to have a little bit of energy, you provide a little bit of energy, it will always try to find its minimum energy states, which should be the solution of the problem that you try to map onto your hardware system. And the classical computers try to do that job because they notice this powerful approach to solve problems. But the issue is that with deterministic hardware, our classical computers, they try to implement certain algorithms in order to pretend that they can do this type of annealing algorithm and try to look for the ground state of the problems. But it is still very power hungry and it's very inefficient. And in 1982, actually, famous physicist Feynman, he is always being credited as the father of quantum computing, because in his 1982 keynote speech, he has mentioned that he would like to build a quantum computer to solve quantum computing problems. But actually in the same speech, there is, he also actually talked about the probabilistic computer, which is not very well known by the field. People somehow all focused on the quantum computer side. And he actually said there are many problems in our nature are probabilistic, having probabilistic nature. And in order to solve these probabilistic problems, he would like to suggest to build a probabilistic computer itself has elements that are probabilistic. And that's exactly what we are doing these days, actually, with Professor Datta and Professor M. Zeller and also many other colleagues in the field. We are trying to build like a probabilistic computer that can operate at the room temperature to solve all these problems that the classical computer cannot solve. At the same time, we have many colleagues, including colleagues at Purdue, like Professor Mike Manfra has a Microsoft quantum center that is trying to prepare the materials for quantum computers, right? And you guys know that Google, IBM, many companies are trying to build quantum computers. So like in the future, I'm not sure how many years, maybe 20, 30 years, we should actually have all these three types of computers in the field, right? Classical, our current computers, maybe probabilistic computers can come earlier because these are going to use our classical phenomenon at the room temperatures, while quantum computers, if they ever get built, it will be operating at the low temperatures, right? And so I finished the research topics that I would like to attract you to join us. But then another part that I'm serving as the Associate Director of Research for Berk Center. And the Berk, like even now, after it has been built like for 12 years now, Berk is still the largest, has the largest clean room in our nation, actually for all the universities. So we have the largest clean room and the best, one of the best nanotechnology centers that, for universities in the nation. And so that's why I really encourage you after COVID, like come to our Berk, like we have either the NSEC Student Association that can give you a tour of our Berk, or if you contact me, I can also ask my students or myself actually give you a tour of Berk. And so currently our Berk actually has 56 faculty being affiliated with the center from different departments and different colleges. And we have 35 staff members. If you join any faculty who worked in Berk, actually you can access our clean room, our labs, and you can get trained by our very professional staff members to have all the skills to use to operate the tools. And we currently have more than 200 graduate students and undergraduate students actually working in the center. And these are some of the tools that if you are hands-on person, I think that at least myself, right, when I was a student, I saw the instruments and I get very excited because these are exactly what I like to do, use my hands to produce things. Like these are the clean room environment. You can use the lithography to make the tiny devices I showed, or we have all state-of-art type of measurement equipments that you can use to measure your devices and your materials. So this is the end of my sales pitch that I really hope that I convince you this is a very exciting field to work in. Thank you.
That was a very enlightening presentation. I do have a real quick relevant question.
Sure.
That was in chat. Do you need or can you visit Berk right now with an appointment, or do we have to wait for COVID restrictions to lift?
Currently, we do have the social distancing requirements, and also a lot of labs, they don't allow visitors. So right now, if you visit Berk, I can show you around outside of the clean room, outside of the labs, instead of seeing a lot of details. So if you are very eager to have a quick look, we can still do that. Then you will take a quick walk around the clean room. Clean room has a lot of, you can see here in the left-hand side, right? There are a lot of windows, glass windows that you can peek through to see what are the equipments, how people are working inside, and the equipment, you can have a quick peek. So you can, if you are very eager to do that, in COVID time, we can do that, we can arrange that.
All right, awesome. I hope that answered the question in chat. And a few minutes ago, we had Professor Mayer join. If you'd like to introduce yourself real quick.
Hi, everybody. My name is Teresa Mayer. I'm a faculty member in electrical and computer engineering, and also the executive vice president for research and partnerships here. So I have to say that I'm coming in pretty cold, so I don't really know too much of the history of the group or what the objective is, but it sounded interesting. So I don't know if you could just spend a couple of minutes bringing me up to speed.
Yeah, so the Electrical and Computer Engineering Student Society, ECESS, we host events like this from time to time. We try to do a few of them every semester just for professors to be able to talk to students and students to be able to talk to professors in a more sort of informal setting. And we typically theme them around particular research areas. So this week is nanotechnology and microelectronics.
Great. And so these are, are all of you seniors or juniors or a mix? Any?
I am a junior in electrical,
okay,
with minors in material science and history. If everyone wouldn't mind introducing themselves again real quick, we had a pretty diverse range in terms of years.
I can go real quick. My name is Ryan, and I'm a junior in computer engineering. And yeah, I think everybody's kind of all over the place in terms of what they're doing and their year and whatnot. I think there's a couple freshmen as well.
I don't know who said that. Nick, I guess you're unmuted. You can go.
Oh, okay. I'm Nick. I'm a junior in electrical engineering, where I'm focusing on micro and nano.
My name is Edmund, and I am a sophomore in electrical engineering. Hopefully, I can figure out what I want to do next.
Hey, I'm Sam. I'm a sophomore in computer engineering, and I kind of just wanted to learn more about nanotechnology today.
Hi, I'm Jaydeep. I'm a sophomore in electrical engineering and minoring in chemistry, and I hope to, I intend to focus on microelectronics.
excellent.
Hi, I'm Rohan. I'm a freshman going into E, and I haven't chosen between like the MACS side of ECS versus physics, but I'm still exploring.
Wonderful. Well, it's great to meet everybody, and it is a diverse group. So thanks for your interest. And I'm coming slide free today, and was just hoping to engage in more of a dialogue. I can talk about a couple of really exciting, very large programs. I think Zihong gave you a really great overview of a lot of, she covered a very broad scope of the different types of research that we're doing here at Purdue. My own background is in this area. I've just returned to Purdue about 1.5 years ago. I was a grad student here many years ago, and spent most of my career at Penn State, and then did a short stint at Virginia Tech in a similar role. And I'm really excited to be back at Purdue in this new role. Undergraduate research is really important, a very important part of our overall program. So again, for those of you who probably aren't as familiar with the university kind of top level organizational structure, the office that I oversee is responsible for the entire research enterprise. So we look at everything from the interdisciplinary research centers and institutes to making sure that we support our faculty with the preparation of grants and contracts, working with industry engagement, very strong portfolio of federal engagement. So we both look at the strategic as well as what we say, keeping the engine running for the research enterprise here. And again, it's really exciting to be back at Purdue. We have some of the, I think, best facilities in the country to support the microelectronics and nanophotonics area, and have really put them to great use. We have leading programs across the board. It's been really, I think, enlightening as I've come back and saw the diversity from looking at everything from really early stage modeling of materials and devices all the way up through the end system applications for those materials and devices, and really everything in between. So when we think about microelectronics, it is looking at advanced devices, but it's also collaborating with material science and mechanical engineering to think about how we package them, how we move from 1D to 2D to 3D integration, and then also with the increasing heat that's being produced, how do we keep all those chips cool? And we have leading centers in all of those areas. I don't think that there's another university that spans that range. We have national level centers that are looking across that whole range. So again, it's an exciting place to be. I also want to highlight that we have a couple of great opportunities that have just emerged for those of you who are still early in your career. We have a new program that's called SCALE, and this is for undergraduates who are interested in microelectronics. And we have a couple of different thematic areas within this to do kind of a really more focused deep dive. And maybe you've already talked to Peter Brummel. So if he's already gone through this, I won't repeat it. Did Peter talk about SCALE?
I believe he talked about it briefly in one of our previous lunches, but it can't hurt to talk about it again. Okay, yes, repetition can be good. The federal community, in particular, the Department of Defense and the national security and the whole defense industrial base, so companies like Lockheed Martin, Raytheon, Northrop Grumman, but there are a bunch of small companies, have really elevated this area of microelectronics and trusted and assured microelectronics as a big challenge for the country. If you've been following the national news in this area, even recently, there's been such a limited supply chain that manufacturers like the car companies aren't able to get chips, so they've had to suspend operations. So there is a huge interest in really continuing to build and rebuild capacity in the United States to support
advanced manufacturing in the semiconductor area. But also as we think about the supply chain, as we think about ensuring that the chips that are being produced can really be trusted. And when you're dropping them into autonomous vehicles, that's really very, very, very important. When you're dropping them into military systems, it's really important that we have control over the supply chain and that malicious intent is not embedded in the chip. And so this effort is really looking at addressing that. And we have a number of different thrust areas, but it is open to undergrads. So if you are interested in doing a deeper dive, there are experiential learning opportunities. We're partnering with a number of companies as well as federal agencies to offer internships. And the goal is to have those internships throughout your career. And really expose you to the different opportunities in this area in the hopes that we will have more students taking an interest, because the job opportunities and the demand is very, very great. And I think we're experiencing a little bit of pressure at the undergrad level where AI seems to be really sexy right now. But just remember that without the underlying chips, all of those AI algorithms aren't going to work very well. So there's a tremendous need and a tremendous interest, and this is very, very important for our country. So I encourage you, if that's of interest at all, to reach out to Peter Brummel. He's leading that effort. We have a joint effort that is co-funded by industry that's at the graduate level and is providing research opportunities, but those research opportunities are available for undergrads as well. So that's a $19 million effort that we're organizing with a number of other universities across the country. So you'll get a chance to meet students all over the country as well. But anyway, I'm just happy to answer any questions that you might have. My own research right now is in nanophotonics. We're looking at really advanced how you nanostructure materials to make very, very high performance optical components and coatings. So we really push the limits of fabrication, very much like using the facilities that Zihong was describing to you.
I will have to interrupt really quick before questions. I'm pasting that link in chat once more for anyone who hasn't followed it to record their attendance to the event. SAO requires it, or else they get mad at us, and we don't want SAO to be mad at us.
No. Anyway, any question on the enterprise is fair game.
I have a question if no one else does. With scale you were talking about, I know TSMC is building a fab in Arizona. Are they part of that initiative, or are they doing their recruiting separate from scale?
Well, so there are two great questions. There are two interleaving programs. I talked about scale because scale is really focused on the undergraduate curriculum and experiential learning and internships. There's an interleaving program that's co-funded by the federal government together with industry, and our lead industry partner is TSMC. So keep your eyes peeled if you monitor Purdue today. A press release should be coming out in the next 2 to 3 weeks, because we're kicking off what's called the Center for Secure Microelectronics Ecosystem. 2 of our EE faculty are leading that, Jorg Appenzeller and Anand Raman, oh gosh, Zihong, how do you pronounce his last name? Raghunathan, there we go. I need to look at it. My apologies, I work with them all the time. They are co-leading the center. And again, TSMC is investing $1 million a year to support research. But what they're also supporting from an in-kind perspective is multi-wafer chip runs and advanced technology nodes. So for those of you who may have an interest that spans devices all the way through circuits, that's a really great opportunity because we'll look at those really advanced technology nodes. We are very actively recruiting additional corporate partners. Synopsys, which you may have heard, they are one of the leading EDA tool vendors. Synopsys has just joined the consortium. And we're talking to companies like, again, Microsoft, Intel, Lockheed Martin, and many others. So it's shaping up to be a really nice consortium. And the beauty there is throughout your career, you get to work hand in hand with the companies, and the companies are really helping to define what those big questions are. And they're providing, again, both financial support as well as in-kind support. And they are always looking for great interns.
So I suppose that leads naturally into the question of what are they looking for? I mean, what sorts of things should students be doing to get into this field and stay in the field and do well in it?
Yeah, well, again, across the board, the companies are looking for a very, very wide range, but not just the companies. I mean, we also are experiencing a critical shortage in leading talent to support our federal laboratories, both within the Department of Defense, the Department of Energy, NIST. So all of our federal laboratories are looking for the best and brightest talent. And you know, it's really difficult to say. That's such a big question because there are so many different areas, ranging from fundamental materials, looking at new material systems to give higher performance devices, to the design of devices that are driving, you know, beyond state of the art, all the way through to the circuit design and integration. So it is a really, really broad area. I think we bring in companies to also engage with students. I don't know, you know, Purdue is a strategic partner with many of the companies. Intel, we're one of a handful of universities that has a strategic alliance with Intel. TSMC, again, we're one of the few universities that has such a big partnership with TSMC. We just signed a strategic alliance agreement with Lockheed Martin that was announced about 3 weeks ago. Again, you try to keep your eyes peeled and look for opportunities that when the companies are coming to do recruiting, as well as our federal agencies are coming to do recruiting, it's a great chance for you guys to get involved and ask yourself, you know, what are the different things that you're looking for? The other thing I'd like to highlight is that our partner Crane, so for those of you who might be from Indiana and Southwest Indiana, we have a Navy facility, Crane, and they are leading the country in radiation hardened microelectronics. That's critically important for military systems. It's also very, very important for space applications. You know, so applications of satellites and the whole space arena is growing in importance. They are sponsoring another hackathon, and they're really looking for students to engage in the hackathon. So they're, all I can say is this is a really, really hot area. There are lots of opportunities for you to engage and just get a sense of all the different possibilities that are available to you. So sorry, I can't pinpoint it because it really does cover a very broad base.
That's understandable.
But you're at a great place for this area because there aren't too many universities in the country that have these deep partnerships. I mean, the companies are coming here and the agencies are coming here. They're funding work here because we have leading faculty across the board in all of these areas. So you're in a great, great place. but you already knew that.
Do we have any other questions from students real quick? Or real long, that's fine too.
I have a question, or kind of like a ask for advice thing. It's so I'm currently involved with two groups on campus. One is Professor Weiner's quantum photonics group, and the other group is on the with Professor Sundaram or in controls in EC. And with Professor Sundaram, it's kind of like a CS controls and AIML group. And I feel like in the photonics group and on the like physics E side of EC in general, I feel like the learning curves a whole lot steeper as opposed to on the, I would say, math CS signals controls side. And I was just wondering what I could do to like learn better on this side, learn better and do better, can contribute better to research on this side, while like still a freshman and sophomore.
So I wasn't able to hear all of that. So you're considering opportunities in quantum optics, as well as and another opportunity that sounded more like controls.
Yeah, I'm involved. I'm currently involved with both through like the so with Professor Weiner's group in quantum optics. We're building. So right now we're still just building an FPGA for one of their experiments to analyze data. But for instance, the papers that my mentor and Professor Weiner are sending on are recommending for that group and for our work in that, I understand maybe 5 to 10% of the paper, whereas like for the controls group, I understand a whole 20% to 25%. So
yeah. I can relate to that. That's a really so what is your question? How can you?
Yeah, how do I learn? How do I learn enough about the physics and E side to start contributing, to start reading, be able to, okay, let me rephrase, to start being like able to read and understand the research slightly better, and to be able to contribute in like the quantum optics group or any other group.
Yeah, that's a great question. And I can just share my experience over 30 years of engaging undergrads and grad students, and say what you're experiencing is par for the course, because you know, the advanced research is at the bleeding edge. And so it takes a while in order to come up to speed. So I would really recommend maybe the grad students can give you some introductory review articles and more of the popular literature that is written more to the general public, because that's a really good way to start, just to get a better appreciation for kind of the state of the field and what some of the, you know, really exciting topics are. And, you know, that as you continue to take the coursework, then you will become more familiar with the in-depth theory. But my recommendation would be that you try to find, again, some popular literature, but also there are generally very good review articles. More familiar with the quantum photonics area, this is, if you look at what we're calling now industries of the future. So if you're tracking some of the, again, at the national level, the artificial intelligence, microelectronics, quantum quantum photonics, quantum science, information science more general are three of the top industries of the future. And so there's quite a bit of, again, I think really high level literature that can be very helpful to you. But don't get discouraged. Again, it tends to be an iterative. You just, every time you go to a group meeting, you learn a little bit more and you learn a little bit more. And over you know, a year and 2 years, you'll be surprised when you look back and say, oh, wow, you know, I picked up more than I realized. So that would be my recommendation. I don't know, Zihong, you probably have other good feedback.
Yeah, I echo with what Teresa said. I think time is the essence here. We all started from this stage, and like a feeling I know nothing, and go to the group meeting feeling really worried that I cannot learn anything. But actually, really, time is the essence that we all learn and we all grow up in the career path. And another, like besides what Teresa mentioned, I think getting some references, review articles from maybe senior members in your group, I think like team up with graduate students, like following 1 or 2 of active graduate students from Professor Weiner's group would be very helpful. Like I did have undergraduate interns in my group in the summer too. And then like, of course, they always feel like very shy and not daring enough to ask questions in the group meetings. But then I noticed that they actually talk to my graduate students very often, like privately, and then learn from asking any basic questions. Actually, it's very important. And if you have close connections with 1 or 2 of the graduate students, that's very, very helpful. I think that's a good cutting point.
Yeah, and I always found it's really great for the grad students too, because when we're deep in our research, we oftentimes forget how to communicate. And so the questions that you ask will be a great learning experience for them as well. Mm-hmm. I'm going to have to jump off to go to another call, but it's been great. Thanks for the great questions. And you know, again, feel free to reach out. There are lots and lots of things going on. We've only scratched the surface.
Teresa, thank you for sharing a very, very valuable time. I know you're super busy.
I love engage. This is part of my job that I don't like. I don't get to engage with students very much anymore.
Yes, thank you for coming.
Yeah, thank you. Bye.
Bye. Any other questions? Wow, you guys got the Teresa on board. You know, like even us, we Berkeley faculty try to get her time, we have trouble. You guys are really priorities. I can see that. That's great.
And we do have about 15 minutes left. If there are any more student questions.
Any questions, I'm glad to answer any questions that you come up with.
Well, and if the students don't have any questions, perhaps you would have one for us.
So, like I know, like these days, a lot of CSCE jobs, it's easier, right? Or there are a lot of opportunities, and it looks like some of the jobs are highly paid. And so I can see that the shift of the student body from EE to CE. And so, like, what is your evaluation? Like, what attracts you? Is that finally the job pay, or it's the interest of the area, or something? Can you give me a little bit of your perspective?
Yeah, I suppose I can talk about that, and then we'll see if any other students would like to share. I am electrical, as you mentioned, and I noticed that same thing, especially in my sophomore seminar last year. It was amazing. We probably had 50 students in the class, and maybe 10 of those were electrical, and the rest were all computer. Mm-hmm. And personally, I think part of it is that it wasn't super clear to me coming into Purdue the difference between computer and electrical engineering. They were both sort of this nebulous crossover that I couldn't make a clear distinction between. And ultimately, I settled on electrical because I thought that was a little more broad and I could do more with it. Where computer to me seems a little more specialized and almost computer science-y where it's a lot more algorithmic stuff, which is just kind of not my thing. But I think that a lot of that is the general draw to computer engineering, is that disconnect between what is understanding what it really is, beyond just knowing that it's like if you took computer science and electrical engineering and stuck them together. That's a lot of the understanding that I hear from people.
Mm-hmm. Mm-hmm.
Yeah, and
I'm
go
kind
ahead.
of with Andrew on this, because like I did the sophomore seminar and it seemed like you were outnumbered 1 to 5 in everything, in just every classes. If you talked to someone, you could almost assume that they were a computer engineer in all the classes that overlapped. And the main thing that drew me to EE is that the aspect of hardware and working more with hardware than rather with software, because I've always liked the hardware parts of everything, like working on labs, doing everything like that. I always found hardware to be very interesting. But a weird thing about everything is that I'm also double majoring with computer science. So being able to have 100% knowledge in hardware, but also no software, it just feels like I don't even think I'd be allowed to do compy with that. But like just knowing both aspects of everything, I feel like I have a good draw on what's happening and what I can do, and that's kind of focused everything into micro and nano for me.
Mm-hmm, mm-hmm. Yeah, certainly. If you have both sides knowledge, that's definitely a big plus. Yes, I agree.
And no, sorry, go on.
Oh, yeah. So in my experience, just from, I know a few people that have switched from EE to compy, and the labs that sophomores take sort of push them away from EE, just because they viewed it as like really tedious and complicated, and it takes up like a ton of time. And they're thinking, well, if this is like what I'm going to be doing in life, I don't want to have to do this.
Which labs? Can you tell me which lab that just scare people away?
I think it's 2007 and 2008. That
2007 and 2008.
At least just from people I've talked to. I don't know if that's the general consensus, but I know people find some of these tedious. So
okay.
Yeah, I'm taking 2008 right now. I can attest to the fact that it can be pretty tedious at times. But I think that, like, for me at least, the reason I chose EE instead of compy is more like, I think what Andrew said earlier about like how it was more broad. At least when I was choosing majors, it felt a bit more I didn't want to really specialize in a certain part, so I felt like EE would be better for me. And but and also like I enjoy like the hardware aspect a bit more. But I still like the software part. Like I'm taking in my degree plan, I am taking a lot of like compy core classes as my EE electives. So I think like I can get like a good mix of the hardware and software both while still maintaining a EE degree.
Yeah, I think for you guys as undergraduates, like at this point, having broader knowledge base is very, very important. And then especially like for the new computer that schemes that I have described, actually we need both. And if this new probabilistic computer, Professor Data actually, he was more focusing on materials and the device transport in his earlier career time, but now he's much more into the algorithm design, because of any new type of computer schemes need both. You need the fundamental hardware elements. You also need the new algorithms to be implemented to these new elements. So like knowing both sides is definitely beneficial. Like learning is never, never bad, right? Learning is always a plus in my mind. So. And then like I just feel like if the job opportunity is the main reason for some students to switch to the CE side or CS side, I would say that's a wrong perception. because exactly what Teresa has mentioned, and also what I have noticed, there was just so much emphasis in hardware, microelectronics, and so like these days, all the companies are just hiring like crazy, and it's going to continue for many, many years. While for CS side, I see almost every major universities have expanded their CS program. So we will have tons of software engineers out there, right? And eventually the job market has to saturate. It cannot be, the job market just keeps increasing forever. So I think this is also something I notice. It's out of our control. Like, of course, you can say currently this is a hot job market and I'm going to pick that major. But is that going to last in the next 20 years or 30 years? Because we need to work in the next 40, 50 years, right? For you guys, it's the next 40, 50 or even 100 years. And there is no guarantee that one field can stay hot or stay like a highly hiring or highly paid, these type of things. I haven't seen that. And that's why like picking something that you are good at it and you are interested in, that's the safest bet, I would say. Because you were like, to be honest, every day, nowadays I cannot go to work every day, but when I go to work, I'm really happy because I can, like several of you guys mentioned, like you sense that you want to work with hardware, you sense you want to use your hands, you sense you want to be in the lab, use equipment, right? And if this is your nature, then you don't want to just give that up for something, maybe just potentially it's a hot job. So that's my personal take.
And I can kind of reinforce what you're talking about with electrical engineers being kind of hard to come by recently. I was talking with a recruiter for Bechtel Corporation who does construction last year, leading up to my internship with them. And one of the first things he said to me when I said, oh, I'm in electrical engineering, he immediately said, good, because we have a lot of trouble finding electrical engineers. They're just, for whatever reason, he said, they're just not very popular anymore. And we need electrical engineers for construction, and we just can't find them.
Yeah, yeah. Eventually it's going to flip, you will see.
One other thing I wanted to add is that like earlier we were discussing about breadth, and like I feel like after you get through like the 2007 2008 labs and stuff, and the upper does a lot of actually comes closer to CS, like some of the signals and the information theory side. It actually comes closer to like the algorithmic side of like CS and maths than the some of the upper dev compy courses. So that's why like Nick mentioned the ECESS double, that I feel like, or some combination of ECESS that actually might give me more exposure than just compy.
Yeah, glad that you can apply your algorithm mathematics side to the EE application. That's actually the best combination.
Going off of my earlier question for you, when I asked the different research opportunities for micro, you mentioned on how there was a website, but it's not ready yet. Do you have any like ETA on when it would be ready? And also like if there's a way that I would be able to find research opportunities now for like this upcoming summer?
Yeah, Nick, I think that's a really, really great question that actually we should really, the faculty should really focus on developing the MN area website. We noticed that we are exactly losing you guys because we are not advertising our research fields enough. And with our department having more than 110 faculty now, it's super hard for you to go through every single faculty's website and find out what we are doing, right? So that's really like what our shortcoming is right now. And so what I can do is, because I know who are active faculty in the MN area, so I can assemble a list of these faculties, and every faculty has really detailed websites describing their research projects and and focuses. That I'm sure everybody has, because that's how we actually advocate our own websites to our funding agencies and to external world. And through that, you can actually really read upon what we are working on. Like these actually normally the website, for example, you can visit my website, right? These are kind of written for general audience. And so you can get a sense, is this professor more focusing on nanomaterials or nano devices or more like a chip design? So I can provide this list with the individual faculty's websites and give it to Andrew so that he can share with the group.
And I think I think the easiest way for me to distribute that as well is if you guys would like to receive this big old list, just go ahead and DM me in this Zoom meeting here what your email is, and I'll note it down so that I make sure I can get to you.
Okay, thank you.
And also, I know there are quite a few events that faculty go out to introduce their research. I think the next one will be the open house for incoming graduate students. And I think you guys are welcome. I can contact the graduate office. Like we want to attract our own undergraduates to join our graduate programs, right? And so whenever we have these open house events, like candidates from other universities are coming over, and you guys should actually have the access to our events that you learn about the faculty's research, learn about all these general department policies and the graduate programs that you can already start to learn about and consider the opportunities. So I think that one actually is coming up very soon. I can also share the event time and probably the Zoom link with Andrew. I'm writing down this to-do list.
All right, and we go ahead. Sorry.
Just the last thing, that because I have joined it's called undergraduate mentoring program. I don't know if the department has announced that to you guys or not. So like each area, there are quite a few faculty signed up. For example, for an MN area, I know like 7 or 8 faculty signed up, and these are like so we are opening up our calendars on Boiler Connect. And you can see when we are available, and you can reserve a half an hour time block to talk to different faculty. And for example, I volunteered to talk about the career opportunities, talk about the research, talk about the graduate school. Right? These are the things that I'm open for any questions during my open slots. And I know like quite a few faculty from MM area sign up that you can find their slots and talk to them about their research areas too. That's a new program that we are launching this year. I don't know if the department has officially announced it or not, but I know it's ongoing. So
that actually sounds like a very good program.
Yeah, it's called the undergraduate mentoring program.
Yeah.
So every area has the faculty signing up that you can get more information. Yeah.
That is very cool. And I believe that's a good note to end on. It is 1 o'clock, and I don't want to keep everybody too long here.
Mm-hmm.
So unless there's any closing thoughts from everyone, then we will go ahead and sign off. Thank you all for coming. This was a very, very good operation.
Thank you, Andrew, for organizing this event. And thank you, everyone, for attending it. And I'm very happy to talk to everybody.
Thank you.
Bye.
Thank you.